Alright, so I want to talk about models, theories, and laws and principles. Now, we're going to use the book's definitions here. We're going to find that science has to take a very specific definition to versus the English language. And you'll sometimes hear, especially around the evolution debate and sometimes around relativity, that they're just theories. Well, the theory in the scientific world comes from the realization that scientists had that we don't know everything, and we never will. But we can know things better. So the working system we have, we call a theory. It matches the data we have. It predicts the future well, but we will learn more about it. And so we own the imperfection of what we can see in reality. And we will go into the nature of observation and truth of reality, because that's a lot of what physics wants to do. But the word theory in a scientific standpoint means that it is a working set of rules that are predictive of future events based on observed data. I want to use the theory of gravity to illustrate this. Early theories of gravity by Aristotle assumed that everything went towards the center of the earth, and how big things were determined how quickly it went. Galileo, by rolling objects, and he might have dropped something off the Leaning Tower of Pisa, but in general he rolled objects, found that they all fell at the same accelerating rate, no matter how much they weighed. Newton brought this into a theory of gravity that mathematically looked like this. There was a force between two objects that was proportional to their mass and inversely proportional to the square of the distance between them. And there was a constant, which we're going to call G, the gravitational constant. We'll learn more about this, but this was the first full working theory of gravity. And so if we have two objects some distance apart, we'll call that distance r, you can calculate the force of attraction each object will have on each other. So we can say this is the force on 2 due to 1. And so we can also have the force on 1 due to 2. And this theory worked really well. Newton could predict, well, his friend Halley used it to predict Halley's Comet's orbit. They used it to predict orbits of other planets. And they used it to predict eventually binary star systems and the masses of binary stars. And so the system worked really well. And it was a good theory of gravity. A lot of people said, well, you have two objects separated by a distance and they're pulling towards each other. It's a spooky action at a distance, it was called. Spooky action at a distance. And that term will be played later when we have things that operate with what appears to be no means of contact or communication. And Newton said he didn't care why two objects attracted each other proportional to their mass and inversely square to the distance. What he cared about was that it worked, that you can make these predictions. And that's a hallmark of a good scientific theory. Is it has a mathematical model, it makes predictions, those predictions works, and those predictions match observations. It also leaves questions that you need to look at. And those questions later developed, and in it, we found that it didn't quite work with the orbit of Mercury. And certain orbits of some stars were off. And as we came into the late 1800s, it was found that this didn't work when you were really close to very big things. And so Einstein came along, and Einstein corrected it, and he created this equation, which is our Ricci tensor. and our gravitational field tensor. And then this is our constant. Times the energy tensor. And this is the modern field of the modern theory of gravity. These are called Einstein's field equations. And these work really, really well for describing the gravitational interactions of the universe. And there'll be some modifications to the field equations. And that is the current theory of gravity. And this brings us into what's really, really good about a theory versus a model is, for most of what we do, we don't need to use Einstein's field equations, right? I work with the gravity in the Milky Way galaxy, and we use the Newtonian version. It's mathematically simple compared to the Einstein field equations. It's easier to calculate, and it's good enough for the predictions we need to make. So when you choose a model, which is a representation of the predictions you want to make, you choose a model that works for what you need to do. Einstein's theory of relativity, if I plug the right values in, will simplify to newtons when the masses aren't that large. And newtons, when you're very near the surface of the Earth, well, we can say that things fall a distance equal to 1/2. This is a little g, not to be confused with this gravitational tensor, gt squared, where g is 9.8 meters per second squared. And so you'll even find that we don't need to even use Newton's theory of gravity for our models. We can use a very simplified version of it that went back to Galileo. And this is a model that's good enough. And so one of the things that you have to realize when we're working with models, and the model you need to know the limits of the model. The model needs to describe things within the limitations of the system that you have. So when you're really near the surface of the Earth, you can use the 1/2 gt squared, and you will get a very good model. It'll be predictive. It'll solve the problems you need to. But if you're shooting off a rocket, you need to start using F equals g m1 m2 over r squared, and you need to take into account the change in height. And calculus helps you do that. So a theory gives you testable predictions that matches the data, and it works in all cases. A model is a portion of a theory that works for the cases you're dealing with. And we will be using models. We'll be learning the theories and pulling out the models we need to make the predictions. And that's the nature of physics. Now we have a thing called laws. Laws are what we believe to be the truths of reality. They're rules that we can use to build new theories and to build new models. And they seem to be true for all of the universe. The conservation laws, conservation of energy, conservation of charge, conservation of spin, conservation of angular momentum. These are laws, and they seem to always hold true. That goes back to the same question Newton had, though, right? Why do these laws hold true? Right now, we don't care. We observe them to be true, and they seem to underpin a lot of different physics. And we will work our way to these laws. And because they seem to underpin reality, that they're held stronger than theories, and we build theories from them. But theories have predictive capabilities and are a little more mathematically detailed. Models are a small portion of the math of a theory that works for the system we're looking at. And we'll talk about systems more and more. And then we also have a thing called a principle, which is like a law, but I'll say we work a lot with, and the one you'll hear me quote a lot is the principle of superposition. When you have two things at the same spot, you add up what they're doing at that spot. And that principle works really, really well. And so we use that principle when we're building new laws and theories. And so principle, but it's very narrow. It's saying in one location you have two of the same things happening, add up what is happening. And we will see this happen, the principle of superposition. But that's what happens with these different things. We work with models, which are very simplified mathematical subsets of theory, to predict what's going to happen. Models are very limited, but we choose the model that meets the system we're looking at, where we don't run into the limitations. A theory explains a phenomena through all that we can measure, all limits that we can measure. At the edges of what we can measure, new theories are waiting to happen. A law are rules that we seem to see the universe is working to, and we use them to help us build new theories. A principle is an even more basic form of a law. And you'll see that principles and laws aren't proven, but they're the assumptions we use to build these other things out. And that building has been very, very successful in making predictions. And the key to science is predictive capabilities. If we can predict the future from our observations, that helps us, because then we can act accordingly in the future. And that is what